So today we are going to be talking about chapter 13. I'm going to probably get through most of it. It's fairly straightforward, a lot of reactions that we've seen before with just subtle variations to them. The nomenclature is really simple. There's two different types of nomenclature you can have. You can either have simple nomenclature for ethers. So something like this, where we are going to name both halves of what's on the oxygen. So on the left part here, this is an ethyl group. We're counting from oxygen 1, 2. The other side, 1, 2, 3. This would be a propyl group.
So you're telling me that California is overdue for a big earthquake that will cause this?
We're going to put the two halves together in alphabetical order with a space in between them. So this is ethyl, propyl, ether. And these are actual spaces when you're writing these out.
I have what?
This is 3 different words.
For what?
Ethyl, propyl, ether.
Okay,
the other way to do these is, okay, I'm gonna mute everybody. To use it as a substituent. So if you have something that's more complicated, like this here, I'm not going to try to name this 1, 2, 3, 4, 5 carbon chain with a chlorine on 2 that has a certain like RNS to it. So I'm just going to use it as the longest chain, and I'm just going to name this as a functional group. If you have, essentially you're going to name it by the number of carbons with OXY at the end of it. So this is a 2 carbon chain here. It's going to be an ethoxy group. OXY to symbolize that it is an ether here. The rest of it's going to be our normal naming convention. So we're going to want to go through the ethoxy group first. 1, 2, 3, 4, 5 here. So starting to name them out, we have a 2 ethoxy group. We have a 4 chloro. Doing R and S on it, this will give your highest priority. 2, 3. Oops. It's going to be R. So putting it all together, 4R, E comes up, C comes before E, so 4 chloro, 2 ethoxy, our chain is 5 carbons, so pentane. Pretty simple for naming these. You just do what you normally do with ethoxy or propoxy or something like that. This is actually our newest highest priority for functional groups. So this is going to end up trumping a hydroxyl group. And I think before the exam, I'll give you guys a new list which ranks them in order. I think we do some nomenclature a little later on also. So moving on to some reactions. There are a lot of these that we've already seen. We're going to start off with making ethers, which is pretty straightforward. So the Williamson ether synthesis, which you may have done in the lab at this point, is where you take an alcohol, throw in a base like sodium hydride, NaH. This can deprotonate your alcohol. And then from here, we're going to do an SN2. To give you an ether. This is an SN2 reaction, which means it works really well on a primary center. It works okay on a secondary center, and it works really crappy on a tertiary center. So if I wanted to make an ether like this one here, I'm gonna have to be picky as to which side I make from what. So there's two different possibilities for starting to make this. We could either start from this, which is the left side as alcohol, or this, where we have the right side that's an alcohol. So in order to make this ether, first step's going to be the same, throw in NaH. For this one, you need methyl iodide. For this one down here, you would need tert-butyl iodide. And like I said up here, this is an SN2 reaction. And SN2 reactions really only occur on primary and sometimes secondary centers. So this is primary, this is tertiary. This one is going to be two-hindered. And it's going to give you no reaction. Versus this one that's attacking the primary center can easily do this through an SN2 to give you your product. So something to look out for when you're doing these. It does follow like normal SN2 like mechanisms, and it needs a center that is able to attack. The other way to make ethers is through a reaction we've talked about for making alcohols. So we talked about the way to make an alcohol, and typically use this for when you're trying to avoid a rearrangement. If you throw in mercury acetate, and water, followed by sodium borohydride, this allows us to make an alcohol. This OH here is our nucleophile. I'm just going to write NUC for nucleophile. You'll see this a lot today. We can change this out for an alcohol, and it'll still do the same reaction. I'll go over the mechanism in a second. But if I take mercury acetate, and instead something like ethanol in sodium borohydride, give me the same carbon structure, except now we've added ethanol instead of water here. This goes through the same mechanism. I'll kind of go through it a little bit. Where our double bond can come in, attack one of these mercuries. our mercury can cyclize. From here, our ethanol can come in, attack at our more substituted center. I'm gonna add a loose proton. And then finally, sodium borohydride, give us an H minus. That'll kick out this mercury to give us our product. So it's the same reaction we were doing before. We've just swapped out water for ethanol. And that's how you make ethers. We can degrade ethers pretty simply. I'm gonna go to how you degrade them, and then we'll kind of come back around and do kind of a big review page on these. So they pretty readily fall apart if you throw in acid, especially HBr, HCl. And this is going to do kind of SN1, SN2 chemistry. But essentially, this is going to fall apart and give us bromines on either position that was bonded to our oxygen, and as well as water. So how this happens, we're going to pick up a proton. If we protonate this, this can be attacked by a BR. I'm going to draw it attacking on the left. It really could attack the right one first. It's not really that specific. So if it attacks this one that's on the left first, we get this half plus ethanol. We are still in solution with HBr. We still basically have the exact same molecule. So we can pick up a proton again. And this can either leave on its own and go through an SN1 mechanism, or I'm going to draw it as an SN2 mechanism, where BR comes in, kicks out water, oops, to give us our ethyl bromide. So this guy, plus H2O are going to be our final products. Essentially, our ether just fell apart. We threw in HBr. The water was lost, and we brominated every position there was water on. There is, yeah, so I can do one more of these and then talk about an exception to this. So if I had the methyl or ethyl methyl version of this, Throwing in HBr, heat. I think I forgot to heat up here. Although it'll still happen at room temp, it's just lower. You're going to essentially break this in half at both positions. Get Br plus methyl bromide. Aromatic versions of this are not going to work as well. So we haven't really talked much about aromatic compounds yet. That I think is, it's like chapter 15 or 16, something up. No, maybe 16 or 17. When we take an aromatic compound and throw in HBr, it'll do a pretty similar reaction. But it'll grab this H. You can't do an SN2 on an aromatic ring. We'll talk about why later. But essentially that side is going to be kind of inert. So for these, just our Br will come in to the sp3 center, kicking this out and giving us alpha bromide. So it's a really similar reaction. It's just not going to do the bromine replacement on the aromatic side. All right, so this is pretty much all the ether reactions. I'm going to kind of go through these one more time quickly, and then we're going to move into epoxides, which is kind of the meat of this chapter. That's where we get kind of new reactions. So making an ether,
University of Tulsa.
you can either do it by
Yeah. I live in
NSN2,
Nebraska, University of Tulsa.
NaH, some sort of
That is
alkyl
just weird.
halide. You could do it through addition to an alkene, mercury acetate, an ether, or sorry, an alcohol followed by sodium borohydride. We can degrade them with acid. If we have a regular ether, it works really well. And if we have an aromatic ether, it works okay. We get phenol plus alpha bromide. I am gonna skip to the end of the chapter and talk about thiols really quickly because they are the exact same reactions. And I think they should have been put with ethers, but they chose to do them after epoxides. So thiols, this is 13.1. Sorry, 13.11. And it is, you can make them the same way you'd make an alcohol. So NaOH with a primary halide. You can get an alcohol, you throw in NaSH. You can get a thiol. And then if you want to make a thioether, you do the same thing you would for an alcohol, so NaH and some sort of ethyl iodide here can make us an ether. NaH, methyl iodide can make us a thioether. Essentially, up to this point, anything you can do with an oxygen, we can also do with the sulfur. It's right below it on the periodic table. There are a couple of reactions later on which are unique to it, but for the most part, S can just replace O at any point in time. So let's talk about some epoxides. We learned about how to make an epoxide in chapter 8 very briefly, and that was through MCPBA. So in chapter 8, we talked about how if you take an alkene, throw in MCPBA and water, an acid, H3O plus, this will give us anti-addition of alcohols. If we just do the first step, where we throw in MCPBA, this will give us an epoxide. The second step of this was just opening the epoxide. Let's see. So with the H plus, we protonated it, and then the water came in and opened it. But if you just throw in the MCPBA, it'll actually just stop here. It's pretty stable, and there's a lot of reactions we can do with these. There is one other way to make epoxides. Generally, MCPBA is the one that people use. U-Book talks about the other one, so I'm just going to throw it out there. If you throw in Br2 and water, you can make anti-addition of bromine and OH here. You can throw in a base like NaOH, pull off this proton. This can actually cyclize. To give you an epoxide. Both these reactions work. They both do the same thing. You get the same end product, it should be plus minus. And there's no real difference between them. Once you have an epoxide, there are two different reactions you can do. And they both involve attacking at your epoxide center. But there's two different centers, so we'll talk about what the difference is between them. So we're going to start with this double bond here. Throw in MCPBA. We're going to make an epoxide. This is, the book refers to it as primary and tertiary. You could also call it secondary and quaternary. It's kind of the same thing. Either way, one's more substitute than the other one. From here, if we throw in a nucleophile that is not protonated, so our aprotic nucleophile. What'll happen is this is gonna come in and attack at this more less substituted position. Gonna kick out NO minus. And we can add something to this secondary center. There's a whole bunch of these. I'll kind of talk about them in a minute. But essentially this is, usually it's like Na plus, and then whatever our nucleophile is. The other option is if we have MCPBA, and we throw in something that has H plus and a nucleophile. This is going to change our situation a little bit. This is going to give us a positive charge on this oxygen here. And as we talked about previously, because it's next to such a substituted center, this looks more like this here, where we have a pretty strong positive charge on our more substituted center. So when our nucleophile comes in, it's going to want to attack there instead. And we can open up on the other side and give us this alcohol. So there's really two different products you can get from an epoxide opening. You're either going to open on the less substituted or the more substituted. And that's all going to depend on your reagents. So let's talk about some reagents. So simplest, well not simplest, very simple reagent would be sodium ethoxide. So Na plus, O minus here. We have an Na, so this is aprotic. We're going to add water later in order to protonate our alcohol. So this Na here can come in, do an attack on our epoxide at our less substituted center because we are in aprotic solvent. This will lead to formation of this alkoxide, which can pick up a proton for water, and I'm going to draw it with this Oxygen red here, differentiate a little bit. So essentially, oxygen comes in, does an attack on a less substituted center, opens our epoxide. We can do this with a whole bunch of different reagents. So instead of ethoxide here, if we come in with NaCN, so CN as a nucleophile, followed by water. We are going to get almost the exact same product. OH here, CN here. Like I said earlier, if you can do it with oxygen, you can do it with sulfur. So taking Na and a bioether. We can make a bioether from it. So sulfur can come in as a nucleophile, do the same reaction. You can also do this with the Grignard. So make just a carbon-carbon bond. And lastly, we can do this with lithium aluminum hydride, which will add an H. So H minus. Can come in. And we're doing the same reaction here. So we can break these down, well, kind of put them all together into one table. So starting from our epoxide here. If we throw in sodium and some sort of alkoxide, we can add a ether here, NaCN. Let's throw that there. Let's just add a nitrile to it. If you can do with oxygen, you can do with sulfur. Grignards can do the same thing. And then if you want to come in with just an H, you can throw an LAH. each minus equivalent. This will give you this here. So it's a lot of the exact same reaction. I'll give you guys a second to kind of finish up this table. You can see a lot of you guys are writing it. So these are all the aprotic reactions. Aprotic. For epoxides. The protic ones are going to do just the opposite. It's going to add to the more substituted center. So taking basically the exact opposite. So H plus and ethanol as opposed to Na ethoxide. This is going to make our positively charged version of this. From here, ethanol can come in. It'll attack at the more substituted position because that's more electrophilic. We'll lose an H and get the alcohol or the ether on our more substituted with the alcohol on our less. There's only a few of these you can do. So making another table. Starting from the same reagent. Either HBr or HCl will let you brominate at this more substituted position. H3O plus. You'll let you TAD, could give you two alcohols. The one from the H3O plus is going to be the one that is in the more substituted position, even though you're not going to distinguish between them. And then finally, you could also add in H plus, the one we just talked about, ethanol. We could also draw this one out as H plus, H2O. All of these have some sort of really strong acid donor. They lead to your more substituted. We look back at our other table. These are mostly like Na, or Grignard with counter ions, things like that, where you're just completely aprotic. You're adding your nucleophile to your less substituted end. This is a product table. And we can generally follow this rule, except for one exception, which I'm going to talk about, and then we are going to call it for the day. So the one exception to this we have our epoxide. We have a tertiary center and a primary center. We add in NaO minus it wants to attack at the easier spot, which would be this less sterically hindered position here. There's no charge, there's no reason for it to attack anywhere else. We get this opening where our ether is coming off this left substitute. Same compound, throw in H plus. And water here. This is going to open on the other end. At some point through our process, we made this positively charged. We had a really, this is a more stable position. It built up negative charge or positive charge. If I instead have a less substituted epoxide, so now I have a secondary and a primary. When I throw in Na ethoxide, this is still going to do the same reaction. Somebody asked a question in the chat. Oh, sorry. So secondary, primary, there's no charge on our epoxide. It's still going to go to the less substitute center. The exception is going to be with H plus and ethanol here on this, where you don't have something that's dramatically more stable. In terms of energy, this is not as stable. And because of that, you're actually going to have sterics trump the stability argument. And this is going to lead you to the same product as it would if it was a product. So when you have these less hindered epoxides, they all open on your primary center. We're going to review those a little bit more on Monday. It's Friday. So that's all I have for you guys for today. We got through the vast majority of chapter 13. We will probably start on the next chapter on Monday. I am going to post a new lecture schedule because we missed a day at one point in time. So I can update what will actually most likely be on exam 2. So I will see you guys on Monday.